Welcome to this new podcast of Baipetra very short term course. It is a sub podcast under the Hydrogeek podcast. Today I will explaining about the latest technique which is widely used nowadays to reduce the dimension of modeling parameters. This method is known as principal component analysis or PCA. PCA is a technique that is used mainly to reduce the dimensionality of large data sets by converting a large set of variables into a smaller one. Now, let us take an example. Please, if you look into this position, let me make it more prominent. I have tried to make it more prominent. Let me see whether I can do it or not. Search. I want to edit it. Yeah. So this is the editing part. Let us take this markup. Right. So if I take this sample, this is, say for example, some water samples taken from a wetland or river or anywhere. Suppose two samples were taken and you have measured for each sample the result of DO and the result of BOD. Right? Now, this sample, as it's only two variables, 1 and 2, this sample is a 2D, two-dimensional sample, because it describes the characteristic of samples with respect to two dimensions. One is DO and BOD. The sample is S1, and in this case sample can be innumerable number of samples you can have. But what are the characteristics you are measuring or you are retrieving out of that sample indicates your dimension. Suppose if you are measuring DO BOD, it is a two-dimensional sample. If you include along with DO BOD, if you include temperature, then it becomes three-dimensional sample. Okay, same in the same way, if you have a location data of different places, so L1, if you have, this is one location, L2 this is another location, L3 this is another location. If you have location data of multiple places, then my next question would be, what are the data that you have? And you will say that either you will say, I have the latitude of L1, L2, L3, or you can say, I have the latitude, longitude of L1, L2, L3, or you can say, I have the latitude, longitude, elevation of L1, L2, L3. So when you are saying that I have only the latitude of all the location, then that data set is one-dimensional. When you say that I have latitude and longitude, it becomes two-dimensional. When you are saying I have x, y and z, that means latitude, longitude and elevation, you are using the 3-dimensional and so on. Right? Now, to represent 2D data on a graph is very easy. Correct? Suppose for a group of sample, like our water samples, I have this DO and BOD. So let us say y-axis represent DO and this x-axis represent BOD. Correct? And accordingly, the samples will take a place in this 2D domain, in this 2D plot. S1, S2, if there are two samples, there will be two crosses. If there are SN number of samples, then there will be n number of crosses. Right? But you can easily show them in a 2-dimensional plot. The moment you added temperature, these 2-dimensional this 2-dimensional plot will convert into 3-dimensional plot. Isn't so? So the represent of the location will become a little bit difficult because you have to consider 1, 2 and 3 dimension of a sample. Okay. Now, if you introduce another sample, it becomes 4-dimensional. If you introduce another sample, it becomes 5-dimensional. So, more the samples, more number of characteristics that you have about a sample, it makes the representation of the sample more complex. Because if you have, what I would say, if for S1 you have only DO, then you can say that S1 samples dissolved oxygen is this. So if it is higher, then it is oxygenated water, so it is good. If it is lower, it is non-oxygenated water, it is bad. But when you introduce BOD here, you add BOD here, then you say BOD, more the BOD, it is not preferable, right? The BOD must stay within 0 to 5, preferably 0, right? So you have to consider this. If I say whether this sample is fit for drinking water, then you have to consider the amount of DO it has, amount of BOD it has, and accordingly you will say this is good or bad. Because DO has an impact on the sample quality, BOD has an impact on sample quality, right? Now, the moment you introduce another parameter, temperature, then to represent the quality of this water, S1 sample, becomes more difficult. Now you introduce TDS, more difficult, TSS, more difficult, chloride, more difficult. The more the parameters you introduce or use to represent the quality of the sample, I know it will provide you a very good information about the sample quality. The more the parameter you test, better representation of the sample quality will be there. But it will also invite complexity. Okay, it will also involve cost of processing the data. The simple question whether S1 is good or fit for drinking or not. For only this simple question you have to consider DO, BOD, temperature, TDS, TSS and multiple more. So basically the task becomes very complex. More the dimension you are adding, more complex it is to represent the actual information about that sample. So we use PCA to reduce this dimensionality in such a manner that in theoretical manner, if I say that you have to reduce the dimension to, suppose, from n dimension to p dimension, where p is much less than n, but this p contains enough information to represent that sample. Okay, so uh, what I can say, for a more simpler example, you see, take the example of location of an area. Suppose L1 is the area. Now, if I have only latitude and longitude, then it is enough to represent the location of L1. Z will only give me more detailed information, right? X will give me the latitude, Y will give me the longitude, and Z will give me the, you say, the elevation. Now, if you wish, you can also introduce T, what time, right? That can also be utilized. Then you can introduce the another information, slope, at what slope this location is there, so and so on. More the parameters you add to represent the sample, more complex it becomes. So principal component analysis, what it does is, it tries to reduce the dimensionality of the samples into a lesser dimension, however, without compromising the adequate information to represent the sample. So just take this example, function of x and y, lat and log, enough to represent the location of L1 or rather L2 or any point in the world. Right? This is x and y is enough. And if you want to compromise more, with only x you can also represent location. Right? But if you add z, t, s, then the representation is more accurate. You have more information, but your sample data will become complex. Right? That is why, in Newton's law, Ohm's law, in most of the laws there are assumptions. Okay? If there is no assumptions, you cannot identify a relationship between two variables. It is tough to find the relationship. Right? That is why this P is equals to MF, this relation, is not valid for all the cases. There are some assumptions behind it, right? Like zero friction, okay, and many other relevant assumptions, right? So, take the example of Ohm's law. V is equal to IR, R resistance, I current, V voltage. It is valid under some certain assumptions, like temperature. It is valid only for 20 degrees centigrade, right? Not above it, not much below it. So there are some assumptions. Without the assumption, you cannot create a relationship between the input and output variable. So that is why always remember, principal component analysis will try to reduce the dimensionality, but in such a manner that the adequate information to represent that sample is still encoded by that dimension. Okay, so why PCA? I have discussed this. PCA minimizes dataset variables while retaining the key traits. So thus reducing training time and preventing overfitting in machine learning models. So a train can also be easily identified if your dimension is lesser, right? So because the way we can develop this y is equal to mx plus c model, it is much simpler compared to another model like y is equal to mx plus ny x plus ox, right, plus and so on. So more the dimension you add, more complex the model development become, right? So that is why it is always better to reduce the dimensionality of the model by using assumption or by using this type of technique known as principal component analysis. Now here I will just discuss how to apply principal component analysis to reduce the dimensionality of your data. I am not discuss the background or the numerical aspects of this technique, but I will show you the procedure to reduce dimensionality of a certain set of data with the help of principal component analysis. This is a unique concept. Nowadays it is widely used in various types of studies. So let us see how to do it. Another point that you must remember before I begin to introduce this concept to you, always note that this cannot be done by your hand. This method is not a hand-based method. If you want to solve it by hand, it will take much time. That is why we always use software, okay, to automate the repetitive task. And without the software, you cannot apply PCA within a short span of time. It will take a huge time to apply PCA by hand or by calculating with the help of your calculators. Okay, at least utilize Excel. Okay, and I have suggested one PCA software, one of the most popular software, Excel Stat. Yes, it is paid. I think it cost around, I am not sure, around $295. And there are some free alternative also, but as you know, if you pay, it is always better. The results are always more reliable compared to a free software. So you can download a trial, test the software, and then decide whether you pay it or you will go for a free open source software. Okay. So what is the first step of principal component analysis? After you get a data like this, right? There are S1, S2 and so on, and there are parameters or characteristic of each sample is represented by DO, POD, temperature, etc. Right? So more the number of rows, this sample data become more complex. Okay, so our goal is to, as I am showing an example, I will just consider these two dimension, BOD and DO, and this S1. Okay, so I will to show you to show the how this method works. I am just giving an example that there is a sample whose DO and BOD you know. How to reduce the dimension of this sample? That means there are only two dimensions, so you can, if you want to reduce it, the two can be reduced to one. So you reduce one, there is 2D, you convert it into 1D. Now the main point is you have to decide whether DO gives you the maximum information or BOD gives you the maximum information. Which parameter of water will give you the quality of the sample that you have collected from either wetland or river or anywhere. Okay, so the first step is to standardization of the data set. You have to calculate the value set. How you can calculate? If this is your data, right? If this is your data, then deduct the mean of the data from X, divided it by standard deviation of the data. So as you know, these are most common symbol. This is mean and this is standard deviation. So when you deduct mean from the sample data and divided it by standard deviation, it creates a type of normalization by which the scale difference vanishes. Scale difference between the parameters vanishes. Okay, so this is the first step. Z, to calculate Z or Z, whatever way you refer it, and make a standard data. free of scale differences. So the next step is to find the covariance matrix. So here our dimension is only 2, so we will also have a two-dimensional matrix, covariance matrix. Now covariance indicates, if a covariance between two different variables, in this case DO and BOD, is positive, then that indicates that they are directly proportional. That means if what can I say? If BOD is increasing, then DO will also increase, right? So they have a direct relationship, right? And if the covariance between two dimension is minus, then it becomes inversely proportional. That means when DO increases, BOD reduces. When BOD increases, DO reduces. So that is the case. DO is inversely proportional to BOD in our case. Because if DO increases, BOD will decrease. If BOD increases, DO will decrease. Right? So first step we will have to do the covariance of the dimensions or the parameters that is used for representing the sample characteristic. Now you see this is the matrix, covariance of xx, covariance of xy. Next row will be yx, yy. Okay, so here only two dimension is there, DO and BOD, x and y. So this is 2D matrix. If there are 3, then there will be 3D matrix. If there are 4, there will be 4D matrix, and so on. Now, as you know that covariance of xx or covariance of yy is basically the variance, right? So covariance of x with x is variance of x. That is well known to all of us. But another thing you see, covariance of xy actually is equals to covariance of yx due to the commutative characteristic of covariances. So whatever it is xy, covariance of xy is covariance of yx, nothing else. So if you only calculate the covariance of xy, that is enough, because the other one is just the mirror image of the one side. Because that means if this is the diagonal of the matrix, one side is covariance of xy, another is covariance of yx. So this is basically the mirror image of one side upon the other. So that is the significance of this covariance matrix. Okay, so the law is, why this is same, this is actually the commutative rule of covariance. Covariance of x and y is equals to covariance of y and x, because they are basically showing you the relationship between x and y. Okay, so this is over. You have calculated the matrix. Next is very important thing. It is find the eigenvalue and eigenvector from the covariance matrix. Whatever matrix you have developed with the help of the covariance, you have to now find the eigenvalue and eigenvector of the matrix. Now this is extremely important, because eigenvector will show you the direction of the variance between the two parameters or two dimensions, and how much variance they have in between both of them will be indicated by the eigenvalue. Now all of us know how to calculate eigenvalue and how to calculate eigenvector of a matrix. You see, this is the main relation. A is a matrix. A is the, in this our case it is, A is the covariance matrix. V is the eigenvector. Lambda is the eigenvalue. Again V is the eigenvector. So if you want to find the eigenvalue of this matrix, then you have to solve this one. Determinant of A minus lambda I equals to 0. Here I is a unitary matrix. That means a matrix which have only one in its diagonal. All other data is 0. Okay. Now as we are dealing with two-dimensional data, so two-dimensional problem, so our I matrix will be like this only. 1, 1, 0, 0. That is it. So I is actually unitary matrix. So if you can solve this, determinant of A minus lambda I equals to 0, then you can find the eigenvalue. And if you can solve A minus lambda I V, this V is actually the eigenvector, okay, equals to 0, then you can find the eigenvector. Right? So you can refer to any mathematical book to know how to find eigenvalue and eigenvector, because this is not in our scope to describe about this also. Okay, now the fourth step, this eigenvalue and eigenvector will give you this eigenvalue or lambda. This one is the eigenvalue and this one is the eigenvector. Now this will give you something like V1, as this is a two-dimensional matrix, it will give you something like this, 0.7 and 0.3, and V2 another vector, because of there are two-dimensional, the data is two-dimensional, so this will become 0.3 and 0.7. It is just an assumption or approximation, and it will also give a lambda which can be 0.7, lambda 1, lambda 2 can be 0.3. That is just arbitrarily taken. But this is the value it gives, eigenvalue, and this is the vector, eigenvector. One will give you the direction, another will give you the value. Now this value will be used to find the most significant dimension of this problem. Right? So in this case, if V1 is the BOD matrix and V2 is the DO matrix, you can see the lambda is indicating that BOD is more important compared to DO. Okay, and also if you just want to see how much amount of information is there in between lambda 1 and lambda 2, then just sum lambda 1 plus lambda 2 and divide each lambda by this sum. Again I am saying lambda 1 indicates the eigenvalue of one dimension, lambda 2 indicates the eigenvalue of another dimension. Now if I add both the dimension, it is becoming 0.7 plus 0.3, 1. Now if I divide 0.7 by 1.0, it is becoming 70%, and if I divide 0.3 by 1.0, it is becoming 30%. Correct? So more information is stored in with BOD compared to DO. Okay? So in the next step what we will do, we will remove all the data of DO from this problem. So our problem become from 2D, it will convert it to 1D. From two parameter DO and BOD, as we see that BOD have 70% information and DO had only 20% information, we straight away deduct DO and go on or go ahead with BOD. Right? So this is PCA, principal component analysis, and BOD is your first principal component, PC1. Now there are only two here, two dimension here. If I am working with 10 dimension, and if I reduced this 10 to 2, then the first that have the highest lambda value will become PC1, and the second, which have the lesser lambda value compared to the first, that will become the PC2. If I will just go move ahead with 2 dimension from a initially 10 dimension data set. Okay, now whenever I reduce this dimension, a new vector is formed. That vector is known as, or a new matrix is formed, that is known as feature vector. This feature vector is nothing but a matrix that has as columns the eigenvectors of the components that we decide to keep. Right? So only that column that we want to keep. That means for our case, initially the matrix was like this. Initially the matrix was like this, right? Now we have removed this part, right? So only 0.7 is remaining. Only 0.7 is remaining. This column is remaining. So this matrix is now known as feature vector. And at the last step, the fifth step, just multiply the feature vector, not feature vector, the transpose of feature vector with the standardized original data set. That means the first step. The z values. These z values you multiply with the feature vector. Now you get the final data set which have reduced dimension. That is, whenever you multiply this feature vector with the standardized data set, automatically as feature vector has no DO data, the final output or final data set will only have the BOD part of the original data set. Right? Because feature vector have no DO, so that DO part will get deducted or get out when you multiply the transpose of feature vector with the transpose of standardized original data set. So that is what is principal component analysis. You can use the software Excel stat to reduce this dimension, reduce or to achieve the goal of reducing the dimensionality of large data sets. And for further reading, you can scan this QR code from your mobile phone, and more information you can retrieve. Okay, about PCA. And yes, this software can also be downloaded by scanning this QR code. So with this, I want to conclude today's podcast. Today we discuss about principal component analysis, one of the widely used method nowadays, because we are now dealing with big data analysis, and it is very difficult to work with big data. Big means multiple dimension, n dimension. Always remember, big doesn't mean, yes, number of data is big there, large there, but the dimension is also big. So that is why you must first reduce that big data into small data. Then you must develop your model. If you do that, then the model accuracy becomes better compared to that a model developed based on the big data. It is just like in normal cases, we first delete the outliers of our data set, right? Why we delete our outliers? We can easily include the outlier and develop the model. But as you know, if we include our outlier, lots of uncertainty or extremity or abnormality will be included also. and when a numerical model has to consider all of them, then unnecessarily it will be overfitted or sometimes underfitted also, and will produce a erroneous results because lots of deviated, highly deviated data is involved in that data set. So the model will face difficulty in identifying the trait. That is why what we do, we delete outliers, we also apply that smoothing, moving average smoothing and many other type of smoothing of data. We do all this before starting to develop a model, right? So there are some various prerequisites before you can start to develop a model from a available data set whose relationship is unknown, right? So for that, you have to first deduct the outliers. You have to apply the moving average, right? And then also you have to give some assumption. You have to take some, or you have to make some assumption under which this model will work. Then only you can produce a realistic model predicting a realistic output. With this, I will finish, and maybe in the next episode I will deal with some other techniques. Now, these techniques are contemporary. They may be old, but their use is extremely wide nowadays. If you search any type of database like Scopus or Science Direct or anything, you will find maximum work on numerical modeling is performed with the help of PCA, Principal Component Analysis. Because this is a wonderful tool to reduce dimensionality, and once you reduce the dimensionality of a model, then the development process becomes very smooth, and it becomes very easier to create an accurate model out of that data set. Okay, thank you for now. Thank you for your patience hearing. If you like this lecture, please like and share. Thank you and good night.